Okay, welcome back. What I want to do is to continue with Sittingill's electrotechnical technology. And again, we are continuing with level 3. Now, this is for DC machines too. Now, if you look at the videos I've done already, you'll see that I've done DC machines 1. This is a follow-on to that process, okay? So you need to write out the information for yourselves. You need to extract it. You need to draw out the diagrams. You cannot simply learn this from the screen. I cannot emphasize this point enough to you because you will need to be able to present this in an examination. And when you're sitting there in the examination, you must be able to do the calculations in order to decide which of the answers from your multi-choice is correct. You cannot guess it. Okay. Here, DC machines 2, okay? And again, understand the function of electrical machines, okay? Now ignore the outcome 6 because the outcomes changes, but it still remains consistent, whether it's outcome 6, 7, whatever, okay? It changes depending on which unit you're doing, but the principle of the knowledge is still the same, okay? Now, at the end of the session, the student should be able to describe the principal operation and uses of different types of DC machines. Okay, make sure you come back so I can pan it in. Okay, excuse me. Now, this is just a review of what we've already covered. An electrical machine acts to convert mechanical energy to electrical energy when it is a generator, or electrical to mechanical energy as a motor. Yes, now I noticed, I know, I made, there's 2 holes here, but ignore that, we only need 1, okay? Thank you. Electrical machines always involve the interaction between 2 magnetic fields. DC motors and generators are the same, except the motor drives a mechanical load and a generator uses a mechanical drive to generate electricity. The field windings create a magnetic field within the yoke and pole, and I've covered yokes already in DC Machines 1, so look back at that to see where it followed on from. So just repeating, the field winding creates a magnetic field within the yoke and pole pieces. The armature is the rotating part of the machine and gets its current from the brushes when it acts as a motor, or provides the supply to the terminals if it is a generator. There are 2 ways in which the armature is wired, lap or wave, and I've shown you this in the session 1 for DC machines, so look back at that. Now, the lap and wave becomes more complicated when you're doing level 4 and 5, okay? You then actually have to do the calculations that will give you the, sorry about that. It's okay, I'm just losing my glasses now. That's okay. The armature is the rotating part of the machine and gets its current from the brushes when it acts as a motor, or provides the supply to the terminals if it is a generator. There are two ways in which the armature is wired: lap or wave. Lap windings have as many parts as there are poles, whereas wave windings have only two paths between the brushes. Okay. And again, when you look back at this, you'll see that again in regards to the wave and lap wound, make sure you've drawn up the diagram so you can identify the difference in the two. And you'll find that one is series parallel and one is simply in parallel. Okay, let's make sure we get this on screen in full frame. Okay. Sorry a little bit. Just want to make sure that it's in frame and can be seen at its maximum value. Let me just pan back. Excuse me. Okay, I think that will be it. Okay, thank you. DC machine. Now, at this most basic level, any DC machine has a field winding, which generates a static magnetic field, and an armature winding, which via the commutator creates a changing magnetic field. In this session, we are going to look at how these two windings can be connected and consider the effects of these connections. And here we are, first part, okay? Right, series motors and generators. This is the first way the field winding and the armature can be connected together. And here you can see that, let me move them closer. You can see that here it is a series connection. That's your field winding, okay? And this is your armature, and these are your brushes here, okay? And the IA simply stands for current in the armature. Okay? This is supply, okay? So the current source will be equal to current IF plus current IA. The interesting thing here is to remember that the current in any series circuit is the same current as here, will be the same current flowing through your armature, okay? Now, in a series machine, the field coil and the armature are connected in series. This means that the current flowing in this machine is the same in the armature and the field coil. The armature usually has a high current, and so the field coil must be capable of carrying the same current. So here, your windings in your field would probably be of a higher gauge, okay, cabling, so that it can handle the current in comparison to your armature. So let me just come back a bit. Go up and come back a bit. Oh, sorry about that. Okay, let me just make sure I can get it in screen. Okay, in full. Okay, good. I just want to make sure that it's in, let's make sure we can get it all in. Okay. Okay. Now let's go down to the bottom, just make sure we can now select that section on its own. Okay. In a series wound machine, the resistors are the field coil and the armature windings plus a small amount of resistance across the brushes. The large current means the field coil usually has a few turns of a large area conductor to reduce the resistance. So your conductor might be 4 mil, for instance, okay, or larger in some cases. To increase current control, an additional resistor can be connected in parallel. This is called a diverter. Okay, it's a field diverter. Well, we just simply call it a field diverter, basically. Okay. Now again, bear in mind that you should be drawing out this diagram. You should be making a note of this formula, so you know that the current flowing here in one is the same as flowing in the other. Okay, it is a matter for you to take down this extract information so you understand how it works. Do some additional research specific to this type of motors. Okay. 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 Now, characteristics of series motors. Now, these are characteristics, not exact values, as these change with different motors. Now, the characteristic value is only a guide, because it will depend on the speed of the motor, the current rated of the motor, its applied voltage, whether it's 3-phase or single phase, etc. Okay, so this is only acting as a guide for telling you what it can be. Okay, now here you have, for me here, T infinite to I squared. So T is torque. Okay, so you can increase the torque by increasing the current. But again, T, so, well, you will need to find what you know about the symbol. Okay, but for me, it's just infinite. I'm just going to refer to it as infinite because the current can change. But make sure that you understand what it means for yourself, because you're the ones who will have to be doing the exam. I've done my exams already. Okay. So you have speed, rev per minute, and you have the torque in Newton meters. Okay. Now here we have a shunt wound motors and generators. And again here, let's look at this in full. Okay. Here we have our field windings in parallel with the armature. Okay. So again, the current here is different. It's going to take its own current, and the current in the armature will also be of its own right. Okay. But again here, current source equals IF plus IA. Okay. The only difference here is that the voltage across your field will be the same voltage across your armature. Okay. Now here we have, this is a shunt wound motor. A generator would have an output rather than a supply. Okay. I'll just go back so we can pan this into view. Okay. Okay. Now what I want to do is to go down a little bit and make sure that we can get this bottom section in. Now remember, you will need to extract this information for yourselves and read it through for yourselves. Make it your own. Draw the diagrams. I cannot emphasize that point enough. Get it done. Okay? Do not assume you can read it from the screen. We're not in the matrix. I can't just plug you in and upload this knowledge into your brain. Okay? The problem with that is that as I unplug you, all that knowledge would be gone, and you will still be no use to me as an electrician. Get it done. Right, the field coil is connected in parallel with the armature. This means that the field coil and the armature both receive the full supply voltage. A shunt machine's field coil usually has quite a small current flowing in it. The armature's carries a much greater amount. Okay? Soon after, you can make sure we can get enough read from any angle, basically. Okay, that's the idea, that it is red. Okay, let me just go back up. Excuse me while I pull it back up. And I've pulled it up, okay. And I'm going to pan back. And hopefully we get this into full view, okay. Okay, good. Now again, read the information. Do some additional research for yourselves. Do not just take it as read. And can I remind you, please, safety, safety, safety. And here we have a shunt motor. The shunt motor is considered to be a constant speed motor because the supply is connected directly across the field coil. The flux created by the current remains constant, and so does the induced EMF. And here we have a variable resistor which controls the current to the field. By reducing the current to the field, you can increase the speed of the motor. Okay. And here we have the formula. Let me just move into the formula. Let me just pan back, make sure that we have that there in view. Okay. And let me just go into close to your formula. Now here you have I supply equals current armature plus current field. I supply equals IA plus IF. Okay, current in the armature plus current in the field. The majority of the current will flow through the armature, but only small current will flow in the field, keeping that constant, allowing the motor to run at a constant speed without damage to itself. Okay. Okay, let's pan back quick. Let's see if we can get it in. Let's just get it in. Okay, let's just get it in. It's in frame. Okay, I don't want to. Excuse me. Okay. Now I'm just going to go down so we can get the bottom section in, and again, hopefully making it easier to read. Okay. The speed falls off with an increase in load. This can be compensated for by weakening the flux. To get a better level of speed control, a variable resistor is connected in series with the field coil. The current flows from the supply and divides at the connection between the field coil and the armature. Okay. So all we're saying here is that this variable resistor allows us to increase the current to the field or decrease the current in the field accordingly. If the motor is driving a heavy load, then we need to increase the field current so that the motor can handle that load, because as the load increases, the motor would slow down. So we need to be able to drive that motor at the speed previously by varying your variable resistor, thereby making the field current greater, which allows us to increase our torque. Okay. Okay. Good. Well, I've left it there so you can take time to read it through for yourselves. Okay. Let me just pan back, make sure we can fill this in. Okay. Good. Okay. And here we have characteristics of a shunt motor. Now let me make sure that I can get this into play. Now again, here you don't need me to tell you. You can see how it, the speed, gross torque, and you can see how the torque begins to reach a maximum and it begins to peak off. Okay, in regards to the speed, at a certain point, torque in respect of speed, one or the other will begin to. If the torque isn't sufficient, it will lose speed. Basically, okay. And you need to maintain the torque, and you can do that by increasing the current in the field at a point in time. The series motor, the torque is directly related to the armature current squared. Okay. Speed remains reasonably constant over a wide range of loads. The torque is directly related to the armature. As the current in the armature rises, so does the torque. Shunt motors are commonly used on machine tools, fans, and conveyors. Okay. And here we have the shunt generator. Now I'm not going to talk to you anymore on this because you can now do your own research on this for yourselves. You can do your additional gathering of information. You can begin to draw out these diagrams for yourselves, and again see the formula still stands. Okay. And here we have compound wound motors and generators. Again, here you can read this for yourselves. Okay, let me just make sure that I can get it on screen, and it's easy to read. Okay, that's the idea. Okay, I don't want you straining your eyes wondering what it means or what it is or what it is saying. I want you to be able to see what it is saying, so you can do your additional research for yourselves and get some work done. Okay. Short shunt compound motor. Okay, the field winding is only connected across the armature. Okay, again, here you have, okay, short shunt compound motors. Now draw these diagrams out. Okay, get to know what they are, then do your own additional research. Look at the calculation that goes into this. Now I believe I may have done some calculations of this on a previous video, but I'm going to recheck my information for myself and see if I need to do any additional work to this. Okay. Long shunt compound motor. The field winding is connected in parallel with both the series windings and the armature. Okay. Now you can see the difference between here, where the series winding is, that's your series winding. Let's go back a little bit. And here you have your series winding. So you can see the short shunt compound motor. Look at the difference where your series winding is in this case and where it is in this case, okay? And that in itself makes up the difference. Okay. Okay. And here we're looking at the compound wound characteristics. Now read the graph and look at the levels, okay? Terminal voltage, load current, okay? You can see here, it gives you an idea. Now here is maximum level, and this is where it begins to fall off, okay? And here you have your differential. Now the straight horizontal line is assumed to be the desired speed over a range of loads. That's your desired speed, okay? But you can see that here you have slight variations where it might begin to drop off, and here it begins to defade. Here you have a massive, you have not reached your level that you would require. But speed range of load. The top line shows a cumulative wound compound motor or wound compound machine. The bottom line shows a differential wound compound machine. Okay. We'll go back, make sure we get it into place, okay? And let me just go in close to so we get everything in view. Now read this for yourselves, okay? Draw the diagrams out, and especially draw the graph, okay? You can create your own scale if you want to, okay? Right, here we have separately excited DC generators. The fuel coil has a separate supply from that of the armature. The separately excited type of machine can have a different supply to the fuel coil at a much lower voltage, and the speed can be externally regulated. Now the external supply to the fuel coil creates a magnetic field which interacts excuse me, with the armature, which in turn creates the motion. It is used as a generator, and its output is varied by altering the supply to the fuel coil. The output tends to fall as the load increases. Okay. Okay. And here you have the load characteristics. Now again, draw these out. Get a feel for having in respect of terminal voltage and the load current. Okay. Look at your principles books as well, because it will provide you with a table giving you the load current at a given voltage. And here we only look at 100 volts, when normally we can be looking at 200 and 30 volts or 400 volts out in a three-phase supply system. Okay. Okay, thank you. Now I hope you found this useful. 1. Do some additional research. 2. Draw out your diagrams and circuits. 3. Revise, and safety. Thank you. Have a good day. Bye-bye.